Hello, everyone. This presentation will talk about how to use OpenSky ADS-B data to characterize GNSS interference bands and to localize the interference source. And based on the title of this presentation, you might wonder why are we using ADS-B data? That is because we wanted to develop an capability to rapidly detect and localize interference bands. And having the ADS-B reports from different aircrafts, we could have an overall picture of interference events going on at some target airspace. And for this project, we focus more on events that are happening close to airports. So this type of events usually could cause denial of GNSS-based landing, and we want to protect aircrafts from that. And eventually, we wanted to make sure this project help provides for better situational awareness and safety, and help identify sources and localize them and eventually turn them off. So before I start talking about our research, I'd like to talk about the pie art. So researchers from Eurocontrol, they've been doing similar things. They were able to generate probability density heat map for the localization of interference source. And researchers from New York University, they were able to figure out the distribution curve of NAC to help identify the presence of interference events. And for this presentation, I'll talk about our project from three parts. First, how do we process the OpenSky data? And second, what are the characters we find out for different interference events? And third, how do we manage to localize the interference source? So starting from part one, this is a flow chart of what we usually do for data we queried from OpenSky. And as you can see, we started with querying raw position messages from OpenSky. And by that, I mean, this is how a raw ADS-B position message commonly looks like. And if we convert that one into bits, it would be 112 bits long. And so a second step would be try to follow the rules from MOPS to decode the raw position message. And if you are new to decoding the ADS-B raw position message, I highly recommend read the book written by Zixi called the 1090 megahertz riddle. It has a very nice summarization of the key points in MOPS. And then the third step, which is the most important step, would be trying to standardize the time difference between different ADS-B ground receivers. And why is that important? Because of two reasons. First, ADS-B raw message itself doesn't contain time information, so we wouldn't be able to use ADS-B message itself to figure out what's the time that the message has been received. However, the ADS-B ground receivers could be able to put some timestamp onto the message and telling us when that message has been received by that ground receiver. So therefore, that leads to a second important reason, which is if that ADS-B receiver has been putting some wrong timestamp to the message, that's the equivalent of us having a wrong position information. And what do I mean by that? I would like to show two common problems we've encountered during processing the data. First is some time step caused by inconsistent internal clock. As you can see on the left-hand side, we're showing a table of data, and here I'm adding the identity of the ground receivers. But as you can see, receiver A and B has been receiving same raw message on the same time. But later on, some time later, A and B saw same raw message, but on different time. And you could see that time difference between A and B is almost like 15 seconds longer. So later on, we find out that that's because of the inconsistent internal clock on ground receiver A. Therefore, that leads to A putting some random, slightly different timestamp onto different raw message. And what kind of problem could that cause? As you can see on the right-hand side, I'm plotting the flight path of same aircraft with respect to different ADS-B ground receivers. And as you can see, it's time versus altitude. For ground receivers B to the IF, as you can see, they are following the same path, very close to each other. But for this ground receiver A, it has a flat path that's like slightly off from the mean crowd. And if you plot that flat path onto the 3D plot, you will see a zigzag shape of the altitude because of the different timestamp from A in compared with other ground receivers. So that inconsistent internal clock is one of the problems we covered. Another type of problem would be directly an incorrect timestamp. As you can see again on the left-hand side is showing that ground receiver A has been putting the same timestamp onto 15 different ADS-B messages. And we know that ADS-B wouldn't be able to broadcast 15 different messages on same millisecond. So therefore, A and also later on ground receiver B, A and B has been putting some wrong timestamp onto the messages. And that's how it looks like on time versus altitude plot. Again, it's the same aircraft, same flight path with respect to different ground ADS-B receivers. And as you can see, receiver C to the G are following the same flight path, but A and B are showing some weirdly shaped path. So there's two common problems caused by ADS-B's ground receivers timestamp. Leads to some sort of problems on 3D plot and also gives us some kind of incorrect position information if we didn't filter out those non-standard ground receivers. So therefore, after step 3, step 4 would be filtering out those non-standard ground receivers and also do some final touching to the data, and eventually we obtain this CSV file which contains the information of time, latitude, longitude, altitude, etc., which we decoded from the raw message obtained from OpenSky. So after knowing how we process the ADS-B data, let's move on to what are the characters we identified for interference bands. So we started with having 3 known reported GNSS jam flights happen at Hayward Airport. And based on that, we decided to perform analysis on flights that are flying by Hayward Airport from January to March in 2019 and from January to April in 2020. And as you can see, among those 6 months, we only have 8 plus 14 days that contains potentially jam flights, including those 3 reported jam flights. So therefore, we could say that the interference events happened at Hayward Airport are pretty intermittent. And let's see what we commonly saw at Hayward. So this is a plot of 1 day's flights flying at Hayward Airport. And here the black square is showing the boundary which enclose the target airspace we want to perform analysis in. And the reason that we choose that area is because those 3 reported jam flights were all being jammed around this area here. So therefore, we wanted to make sure the target airspace is enclosing that commonly impacted area. And here on the upper left corner is the location of Hayward Airport. And here the green line is just showing each one of the flight paths that's being flagged by each one of the different aircrafts. And as you can see, most of the airplanes were just passing by this airspace, and only a few of them were trying to land at Hayward Airport. So having this overall picture, let's see what are some characters we could identify. So here I'm showing a time versus altitude plot for all flights that's been flying on January 6th, 2019 at Hayward Airport. And as you can see, each one of the line is representing one flight path from one aircraft. And then they were plotted as dots because each one of the dots is representing one position message we received. And the color of the dots are showing the value of the NIC parameter. As we know, the lower the NIC parameter, the lower the accuracy and integrity of that position information would be. So here NIC equals to 0 is pretty much equivalent to saying the current position information is close to unknown. And so here, most of the flights are showing a NIC value that's larger and equals to 7. And also there's no gaps in between the flight track. Only 2 of them are showing some non-standard behaviors, and here I'm highlighting them with thicker points. So on the right-hand side, this flight is actually one of the 3 reported jam flights we have for Hayward Airport. And on the left-hand side, we didn't receive any reports, but it doesn't behave like what we saw for normal flights. Therefore, we treat this type of flights as non-standard flight, which also we need to pay attention to them. But so far, just let's take a look at the right-hand side, because that one is one of the reported flights. Let's see what kind of characters we could identify. First, you might notice there is a gap in between the flight path, the flight track. That gap, I'm using an imaginary line connecting the 2 points, the starting point of the gap and the ending point of the gap. And here, that duration is longer than 10 seconds. And what we commonly saw is that for normal flights, even though sometimes there would be some tiny, small gaps in between the track, the gap wouldn't be last longer than 5 seconds. So it would be always less than 5 seconds. And for those reported jam flights, as well as some potentially jam flights, they have gaps that are longer than 15 seconds. So 10 seconds here is just a standard with some threshold. And then another property is that, as you can see, there is a graduate NIC variation surrounding that gap. The NIC drops from 8 to 7 to 6 down to 0, and it recovers back from 0 to 6, 7, and all the way back to 8. And that property, we not only saw that one on this flight, we also saw them on the other 2 of the reported jam flights, as well as some other potentially jam flights. So therefore, we could say that, okay, those 2 characters could be some common characters that caused by infringements. But for those of non-standard flights, such as this one on the left-hand side, what are the main causes of those behaviors? We, after run all the flights on those 6 months, we find out there are 2 other main types of non-standard flights, which we summarized here. So first type would be some sudden variation in NIC value. As you can see here, I'm plotting altitude versus time. And as you can see, at some point, the NIC value drops from 9 to 0 within 3 seconds. And the NIC value recovers back from 0 to 9 within even 0.5 seconds. So that sudden variation in NIC value is kind of what we sometimes often seen for non-standard flights, and we wanted to figure out what are the main causes of those behavior. The second type would be a set jump of the flight path. As you can see here, it's a top view of the flight path onto the 3D plot. And the aircraft not only contains some sudden variation in NIC value, also at some point it starts to have the latitude and longitude values scattering around the map. And this type of set jump of the flight path is another type of non-standard flights we all often seen. So later on, we'll try to figure out what's the main cause of those type of behaviors. And now knowing the characters of some characters of the infringement, now let's move on to how do we manage to localize the interference source. So here, the black box is showing the target airspace that we want to perform analysis in. And imagine there is a jammer on the ground that's being turned on. And if we assume that the jammer is omnidirectional and the impact area is perfectly like spherical, and the power is high enough, then we could say that for all the airplane that's being flying past this airspace would be impacted by that jammer and would have some gaps in between the flight path. And here the cross point is showing the starting point of the gap, and the circle is showing the ending point of the gap. And based on our assumption, we could say that for those cross points, they should be somehow perfectly exactly on the boundary of the impact spherical area. However, the circle point should not be exactly the point when the airplane start leaving the impact spherical area. In fact, it should be further away from the impact region. And why is that? Because we know that when the airplane loses the GNSS signals, it needs some time to do acquisition and tracking before it becomes able to recalculate its position information and able to rebroadcast the ADS-B reports. And because of the complicated process of that procedure, here we decided to just use the starting point of the gap, which we assume that it should be theoretically on the boundary of the impact sphere. So here we are using point 1, 2, 3, 4, 5 as our input data. And let's see what does that model looks like. So here, that's point 1. And we have 4 unknown values we need to calculate. We want to figure out the location of the jammer, so the latitude, longitude, and the altitude would be unknown. And also we wanted to know the size of the impact spherical area. So the radius r would be the 4th unknown value. So this 4 unknown value would be what we're trying to figure out. And this point is as we know, it's the starting point of the gap. And we assume that theoretically it should be on the boundary of the spherical impact area. Therefore, here we could use convex optimization. And what we try to optimize is that we try to minimize the distance from the input point to the boundary of the sphere. So that little d is what we try to minimize, because we want to try to make sure that starting point of the gap is on the boundary of the sphere. So d could be calculated by the absolute value of radius minus the distance from the point to the jammer. And if you are familiar with convex optimization, you would probably already notice that the absolute value and the square root value of a convex function is no longer convex. Therefore, I did some modification of this current objective function, and that leads to this final objective function. And the detail of how I modified the previous function to this one would be shown in the paper, but what we can know is that the physical meaning behind this objective function would be same as what we mentioned before. We try to minimize the distance from the outer boundary of the sphere to the input data points. And before we start to apply this model to real data, let's just see how it works in theoretical data. So here we pick 7 points on purposely by ourselves, and those 7 points were designed to be on the boundary of a sphere with radius of 2. So here, as you can see, after putting the 7 input data into the algorithm returns with a jammer located at this point, and the radius the algorithm given us is equal to 1.97, which is very close to 2. And the location of the jammer matches exactly with what we designed it to be. Therefore, we can say that, okay, this algorithm works well in theoretical data. And how about we plug in real data? So now we plugged in all the starting point of the gaps that are happening on January of 2019 at Hayward. So here, as you can see, we only have 6 flats that are having a giant gap in between the flat track on the January of 2019. And as you can see, those 6 points are not scattering around. It looks more like a straight line. So therefore, it's not very good for us to model that impact area as a sphere. But so what the algorithm could give us would be a jammer located somehow in between those 6 points. And let's see how that looks like on a Google Earth map. So here we plot that result onto the Google Earth map. This is a top view. As you can see again on the left upper corner is the location of the Hayward Airport, and the red cross is showing what the algorithm think that the possible location of the jammer, and the giant red circle is showing the impact area, the impact region of that jammer. And you probably noticed this crayon circle is circling an industrial area, which means these algorithms could tell us something like maybe that industrial area might contain some jammers, some interference sources that could cause those interference events. So this presentation, we showed that using ADS-B to provide situation awareness of GNSS interference events is possible, and by that we show how do we characterize the effects of interference events and how we manage to localize interference sources. And for future work, we decided to first try to investigate what causes those non-standard flight dynamics cases that we mentioned before. And also second, we wanted to improve the objective function and jammer model for localizing the interference source, because we know that theoretically it could be a spherical shape, but in real life it would be some different model that's more complicated than that. And last but not least, we wanted to investigate more similar interference events that were reported at other airports and see if there's any new outcomes and new results. And that's the end of presentation. Thanks.